Calculate the efficiency of packing in case of a metal crystal for a simple cubic structure. How do we do that? Well, let's draw first a lattice. A unit cell, as a matter of fact. This looks like a unit cell. And how do we draw a simple cubic structure? Let me draw this for you. What are you up to? I'm just marking midpoints so that I can draw nice, neat diagrams. Oh, this is lovely. It's very lovely. This is a unit cell for a simple cubic structure. As you can see, corners are lovingly touching each other. So edge length A is equal to 2 times R. What is the occupancy of this unit cell? There are 8 corners, 1 sphere inside. So packing efficiency is, what is the volume occupied? Volume occupied is the volume of 1 sphere. So 1 sphere, 4 by 3 pi r cube, divided by volume of entire cube. Entire cube is A. But A is equal to 2R. So instead of A, I could say this is 4 by 3 pi r cube divided by 2 cube r cube. Oh my God, this is pi by 6, which is 0.52, something. So 52%, only 52% is packing efficiency in the case of a simple cubic structure. What about packing efficiency in the case of body-centered cubic structure? Let's take a look. Body-centered cubic structure. Let me draw a diagram for BCC. This is most difficult and ugly looking diagram to draw because that body-centered sphere is always a very huge and enormous ugly looking entity. But well, this is the way it is. Let me make an attempt and draw this nicely. I think I'm doing a good job. Please note, all the corner atoms are actually touching the central atom. Corner atoms are touching the central atom and they may not touch each other. In fact, they would not be able to touch each other. Okay, so what does that mean? It means that if I make a section like this, if I just cut away one portion like this, can I do that? I can. And if I do that, what would I get? See, this is, if this edge is A, if this side is A, and this also is A, see, this is A, this is A, so this is A root 2. Oh wow. And what about this? This also is A. So actually, if I cut away, this is a rectangle. If I cut this away, what I have is a rectangle. I'll draw that for you. It is this. This side is A and this side is A root 2. Oh my God. And I have a huge central sphere and I have corners which are clearly and happily and lovingly touching it like this. Let me draw it in some more systematic and clean fashion. Yeah, this is what it looks like. What about the other edges? This is A root 2, and hail Pythagoras. We have this as R, R, R and R. So this violet line, a purple line is 4R, and thanks to Pythagoras, A square plus 2A square, this is diagonal which is A root 3, and by figure this is 4R. Oh my God. So I have a relationship between edge length A and radius R? Yes. What is the occupancy of this unit cell? Well, occupancy is 2. One at the body center and one at the corners, 1/8 into 8. So if you talk about packing efficiency eta, what would be eta? Eta would be number of atoms within the cube is 2. 4 by 3 pi r cube is the volume occupied by them divided by a cube, right? And what is a cube? A is 4 by root 3 r. So this is 8 by 3 pi r cube divided by 4 by root 3 r. It is cubed. Oh my God, this is such an ugly thing. If you just solve this, you have, I'll just do this for you. This is 8 by 3 pi divided by 4 cube, and cube of root 3 is 3 root 3. 3 cancels off, 8 2s are. So this is pi root 3 by 8. If you solve this, this comes out to be 0.68. So BCC has approximately 68% packing efficiency. Now we have to calculate the efficiency of packing in case of a face-centered cubic or FCC structure. How do we do that? First, let's make a unit cell. How would you draw a proper FCC structure? Draw with me. I think it will be useful. First, draw the face-centered atoms like this. Okay. And what about the corners? We will have the corners. We will not be cornered ever. Just take a look like this. Okay. Oh wow. This is what FCC looks like? Yes, my dears, this is what FCC looks like. You can shade it also in case you want to make it more prominent. Now, there are 8 corner atoms. Yes. And at each corner you get 1/8, and there are 6 faces, half each. The total occupancy is 4. Yes. That means there are 4 spheres within this FCC structure. Fine. And if I look at just this face, I could discover a few things. What? That this side is A. Yes. This side is A. Yes. So this diagonal, this fat, thick diagonal should be A root 2, right? And if you care to see, this is radius R, 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 and R. If it is vague to you, I'll just make this cleaner for you. Oh. I'm just removing the dirt so that your life becomes easier. Now can you see this? A, this is A root 2. So A root 2 is 4R, or A is 2 root 2R. A is 2 root 2R. Such a beauty. Now, efficiency packing. This is, now there are 4 spheres. So 4 into 4 by 3 pi r cube divided by A cube, which is 4 into 4 by 3 pi r cube divided by A is 2 root 2R. So 2 root 2 and cube of that, or 2 cube and cube of, so root 2 into cube will give you 2 root 2. Fine. 2 cube, 8. 8 into 2, 16. 4 4s are 16. Fanciful. This is pi by 3 root 2. You solve this. This is around 0.74. Okay, what does that mean? That means that packing efficiency of FCC structures is around 74%. And that actually is the best packing ever.